I've been following along with Paul McCorders Raspberry Pi lessons, and I because I have a Pi 3, I had decided to sit on the sidelines while he was doing his pan tilt hat. Um, this week's lesson was very intriguing, so I actually took the servo out of the kit that we have and just doing the pan part of it. I mounted the servo horn onto a board and just printed up 3D printed up a little slot for the camera to fit into and attach where the servo attaches. So that turned out pretty nice. But um, so I only got pan going on here, and as you'll see, you can see Paul's got 14 frames per second, which is he's using a Pi 4, I'm sure, and um, I'm down to 4 frames per second, or maybe even a little bit less on some of it. So I know I won't be able to go into the face detection or anything like that with it. But today's lesson, where he was saying, I had followed along in the +1 and -1 on the servo thing was that's way I would have done it in the past and everything, but he said, well, there might be a better way to do it. And I thought, I don't know, because you're converting pixels to servo angles, and they don't necessarily compute, you really don't know what the ratio is or anything. So I thought, well, maybe I can figure out what the ratio is. So let's go to my Raspberry Pi. I got it VNCing into it, and a couple things that are different than what Paul did. One of them, I'm not using the track bars. If you've watched my previous videos, I have it set up where I click the mouse to pick the color and everything. So I didn't have track bars, so I chose a different way. I thought, track bars was a good way of choosing between tracking and not tracking, but there's also the other way we can do it, where we're using our wait key to quit out of our program. We can also just, uh, put the wait key into a variable and then check it against whatever keys we want to press. So what this thing is I'm going to start out with my servo at 0, and then I can either go up or down with it to move the servo, and we can look at how far away from how many pixels away from the center it is. So uh, I guess that that's the big changes. Like I said, I'm using my circle, so I have a center, and it's center of our what we want to get. So uh, I'm using my N/R here to print out our angle and everything. I'm doing a little bit different here. I got the N-R here, but if my angle changes, I got a Boolean variable. If the angle changes, if I press one of these keys down here, then I make the change angle true. And what that does is that as long as the angle stays the same, it's going to keep recording the pan angle and the difference in the target center tracking um, uh, on one line. But if I change the thing, it'll go to a next line. That way, it just makes it a little simpler so that we can, or a little more visual that you can see down here. So the best way to do it is just to run it, I guess. So there's my ball, and like I said, when it starts up, it's already hard coded in to match this ball, but um, I can looks like it might be off a little bit because it's a little bit big. Let's try. I don't want to get it too bright or it'll get in with the lights that we got. There we go. I don't know whether I changed it much or not, but This is called the min enclosing circle. So it just creates a circle with the bound. So if it's getting it, it works pretty well. And you can see down here at my pan angle, I got my servo at 0, and you can see that the target is on this side of screen, so it's 283 is the pixel number at the center of this screen here. So now I can reach in with my hand, try not to mess up the circle here, and I can go up with the angle, and it's moving it towards the center. And you see now we got another line. We'll do a couple of these so that we can look at them and see what's going on. One, no, that'd be good. So you can see that the angle changes. So we go from at 0 is about 283, then it goes to 298. So it's at less than 20 pixels. But then the next one goes to 329, so it's 31 pixels. And you can see the next one is going about 30 some pixels too. So the ratio is not set, and it's not even repeatable. So if I go back now, if I go down, I'll do one. All right, so you had 3, you got here, you got on number 2, you got 329, but here's 345. And up here you had one at 298, and this is at 318. So the servo position is not necessarily repeatable. So you can't say, oh, I'm just going to go right to that servo. I'm going to that. I can use a hard-coded, 30 pixels per degree or something like that. It just doesn't work. You're going to, be a problem. But you can use that ratio to do it if you're farther away from the pixel. You can, if it's farther away from the center, you don't necessarily need to just go 1 degree at a time. So you can use that. And I just decided that, I was going to use 50 as my, I didn't decide that. I started with 30 because I thought that was a good number. And 30 pixels ended up being, too much, so that, that you're dividing by it. So let's quit out of this. We're going to Q to quit out of this. And like I said, then we're going to go to the tracking one. And let's see. It's all pretty much the same except for on here. Like I said, I got tracking, and I got picking the color. So if it's a P for picking color, or training, whatever you wanted to call it, and but T is for tracking. So I had to have a different starting thing. So picking color is what that's considered to be. And that's the only difference down there. And then up here in the code, we're using this line here where we're taking the width divided by 2, which is our screen width divided by 2. And we're taking the center TC. That's what I get out of this. When I do the min enclosing circle, I get a XY coordinate for the center of the circle, but it's in it's in floats, so you have to do the int to get it out of that. So you have to still get it into integers, and but that gives us a tuple here for the center of our object that we want. So what I'm doing is in this one here, you got the X and the Y in this tuple. So the X is the 0th element. So I'm subtracting the width divided by 2 and then subtracting that out of it to get our error. our pan error. But then I'm dividing all that by 50 because that's in pixels. So if you divide by 50, then it's going to give you a smaller number, and you can use that as the number that you move your servo. It's your angle, so it equates to angle. So the farther, like I said, so farther away, if your error in here is 200, then you're dividing by 50, you'll get 4 pixels down there, or 4 degrees of movement, and it'll move 4 degrees of movement. But then as it gets closer, because this is going through, looping through all the time, and as it gets closer, it's going to reduce that. It might only be 100 pixels by the time you do the second one and the third one and everything. I just thought that, that would be the way to do it, and you could get it that way. And I also, like I said, and then we added the tracking. So if tracking, we're actually setting our pan and tilt angle. I mean, our pan angle. I don't have a tilt. So we're just pan angle plus equals. So that's pan angle plus pan equals pan angle plus pan error. This is just a shortcut we use. And like I said, if this happens to be a negative number, then it's going to subtract it, because a plus a negative number is like subtracting. So that's going to be fine. So we got that, and that's all we're doing. But we're only doing that if we're tracking. And we can see how that works. Let's get this one running. All righty. So we got the ball. I always like to train it a little bit better on our numbers. You can see when I click my mouse, this is the pixel color at the mouse, the BGR. I don't know whether I don't know if that's in the BGR or that's RGB. I'm not sure. But anyhow, it's the pixel color that we need. And you can see even before we started tracking, we're at 8 frames per second. When we're tracking, that's going to go down even lower. So we'll see what that does. But you can see down here that we're also printing out what the distance, how many degrees we're going to be moving if we're doing that. If we were tracking, we would be trying to move 7 degrees to get to center because of how far away from center it is. I can actually move this and it should go down, right? So now we're in the center, it's saying 0. Oh yeah, another thing I forgot to say is that with having that 50 in there and we're just inting it, so we're knocking off the fractional part of the number, we don't need that dead zone. It automatically puts the dead zone in there, which is kind of cool by doing it that way. You see, the farther we get this way. So that's how it works without having the tracking on. But you'll see these numbers, they'll go, as I move the ball, it'll go up and then it'll come back down and eventually settle on 0, hopefully, if it's working. So I'm going to reach my hand in. My camera's on one side of my computer and the ball's on the other side just so I can see it. You see all my junk over here. Got the vacuum cleaner handle and everything in the room. My hobby room turns out to be the storage room for a lot of stuff. So sorry about the mess. Anyhow, so we're got that. So I'm going to reach in here and I'm going to go to T. And you can see that it kind of started tracking on it right away. So if I pick up the ball, see how that number is getting to 1. And if you got up to 4 that time, got up to -5, not -8, and it lost it. Now it thinks it's the light. So what I'm going to do is, it's a little bit not tracking good. I can either click it while I'm doing this, or I could get it out of tracking. So let's try a different color here. See if it thinks it's a light. Yeah, I think. All right, it's going. As long as I keep it in the frame, it's good. I could try a different color since that's close to the green. But you can see it's working. I don't know if you can hear the servo, but I'm not sure I like the servo. When it's doing 1 degree at a time, it's a nice steady move. These, as it goes 5 degrees, it's going as fast as it can, and it kind of just jerks up to that. But anyhow. It's doing what Paul says. I'm interested to see what Paul comes up with as a solution, because I couldn't think of any other, actually. So I hope this is one way or the other. I either got Paul the same thing as Paul's thinking, or I'll learn something new next week when he talks about it. So anyhow, another thing, like you say, when it's out of the frame, if I'm out of the frame, it just loses it. It just kind of just stops until you put it back in the frame. So those that have been following me for a while know that we did AI and did this kind of stuff on PC with a webcam and everything. And I took a little pocket or micro or mini PC that's just them little black boxes you get. Mine was called B-Link, but you can get different models. It's like a $150 box PC that you can get. It's about the size of a big slice of bread and maybe 4 slices thick or something like that. It's maybe 1.5 by 5 by 5 or something in inches. And anyhow, I put that into a robot platform that used like a Roomba type robot that I had won as a gift for Instructables. And I had that, and I did this similar thing. So, but I only actually did the 1 degree at a time on it, or moving it and everything. So I hadn't figured out how to do like moving it more. But one thing that I did with my robot, because it had the pan tilt on it, but for tracking like a ball going around a room or something like that, is that's where these balls actually came from. Because I'll try link to the final product that I had that I showed off at my public library. But the thing is that I tried to keep track of the direction that I was going, so that if a ball went out of frame, it knew which way it was going. And like I said, that round robot could spin in its own, right in place. It could spin in place. So it had actually, instead of 180-degree servo, it could go 360 degrees around. So if a ball went out off of one side of the page, what I did is that I knew which way it was going, so I kept spinning the robot. So worst case scenario is that it got it wrong, and it would spin around until it found the ball. If it did a 360 or whatever it had to do to come back to the ball. But most times it would know which way it had to go, and it would keep spinning. So that was kind of fun. And I had also, because of like I said, the size of the ball. If it was really small, if the min enclosing circle was small, then the robot would also move forward. After it centered itself, it would move forward towards the thing. And when it got to be about half the height of the screen, that's when it would stop. It would say, okay, I see where the ball is and I'm close enough to it, and it would stop. But that was kind of fun to do. And like I say, I'll link to that. But like I said, I only did 1 degree at a time on that project, so it was kind of interesting to try to figure out, okay, well, you got pixels and you're trying to convert to degrees, and not always an easy thing to, not a, you can see it's not a hard-coded number down there that you come up with. So anyhow, that's my homework for today. Probably a lot more information than you needed, but it was something that I wanted to look at, and I look forward to Paul doing the face stuff on his thing, on his Raspberry Pi 4, but I'll be on the sidelines for that. You can see, well, it's back up to 8 now, but if you notice, it went down to 4 frames per second while we were tracking. So if you're moving it, I don't know, it's staying up around 7 this time. I've seen it, there's 6. Yeah, it'll definitely slow down as the trying at 5. There we go. As the tries to do that. Anyhow, that's my homework for today. Thanks, Paul, for all you do, and have a great day, everybody.